So the structural solver is the product of, I would say, 15 plus years of research at TU Munich. Traditional solvers rely on a meshed approach.
How do you make sure as an engineer you know exactly which one to pick from a ton of different solutions?
Consumer good applications or medical insoles, where we're actually starting to have a significant impact on the lives of people. Phase-changing process due to thermal boundary conditions is quite a complicated task. We all know CFD is expensive. It takes a lot of time. The structural and the fluid solver can be optimized in terms of compute time. So that means you get to your results much faster. Geometric complexity is coming for free. People hardly ever find time to learn a new coding language in their busy days. We provide people with a library of validated materials so that they can easily infill their midsole and create something like this within a few minutes.
All right, ladies and gentlemen, today I have a very special guest, namely Moritz, who is talking about the engineering of the future with Hyperganic. Welcome to the show.
Hi, thank you for having me.
Very cool. Let's maybe start very, very easy. So who's Moritz in the first place and what are you actually doing at Hyperganic?
Okay, so my name is Moritz. I'm the Director of Engineering in Hyperganic. Hyperganic is a software company originally based from Munich, now with headquarters in Singapore, and essentially the second biggest team sitting still in Munich. That's actually where I am today, in our office. We are building software, and similarly we are solving complex engineering tasks for our customers. Generally it looks like someone approaches us with a problem where their current toolset is not sufficient. That means they are searching for more advanced solutions in the additive manufacturing space, for example. That could be a thermal management solution, that could be lightweighting. And we are leveraging our technology stack that consists of a design tool that consists of two simulation kernels, one of them structural simulation, the other one fluid dynamic simulation. And we typically then go and solve these problems either as an engineering service, or we encourage people to use our SaaS products that we have on the market, or we are going to launch rather soon, to essentially solve their problems themselves. That's in a nutshell roughly what we do.
Yeah. We talked about kind of the structural solver, but also the CFD solver, right? Is that written from scratch, or are you using some kind of like quote unquote open foam wrapper and just sell it as the Hyperganic solver? So what's happening behind the scenes?
That's a good question. In fact, we did all the work from scratch. So both the structural solver and the fluid dynamic solver are written from scratch. So the structural solver is the product of, I would say, 15 plus years of research at TU Munich, one of the leading institutes of the world, specifically in immersed boundary methods. So that's the method we're employing here. And similarly, the fluid dynamic solver is a particle-based fluid solver. So we're not using a open foam type of solver, just so that we can use these complex shapes and actually simulate them. Traditional solvers rely on a meshed approach. So a traditional CFD solver, for example, you would always need to go and mesh an object. So you are essentially changing your topology into a finite volume mesh, and then you would simulate this finite volume mesh, which is a representative of your original topology. When you do that, you essentially introduce error into your original design intent. It's not you're not 100% keeping your design intent as originally thought of. So what we're doing essentially through our immersed boundary method solvers is we're eliminating this meshing step, and by doing so, we are essentially forced to write everything from scratch.
How replicable is that approach then? Let's say you have different geometries. Like, is it still like an effective approach at the end of the day?
I would say so. The physics are still the same. So whatever you're simulating is essentially the same. The main difference, I'll try to make it as simple as possible while explaining this now. So my simulation guys, whoever listened to this, don't hit me after this. So essentially, what you're doing in a normal conforming finite volume mesh, for example, you would always take the topology and then generate a mesh that conforms to the surfaces of your original object. While for us, we're essentially turning that around. We're giving you a mesh and we're immersing a geometry into that mesh. But that's all about the big difference between the two. The underlying physics, the way you're imposing boundary conditions, with some small tricks, are pretty much the same.
What are some of the advantages that you get out of such an approach?
I would say twofold. One is compute. Definitely, we can employ clusters. We can speed up the compute by quite a bit. That is because we can, for example, take some of that compute and put it on the GPU, where we are just much faster because you can parallelize compute essentially. The other one is complexity of objects, specifically in the early design of objects. Like, for example, you would infill something with a TPMS, but then you don't know, is this TPMS going to behave the way I want to? And then that's typically where the pain starts for most of our customers, or where people are seeking for an alternative solution, really. So say you are employing a TPMS, and by TPMS I mean triply periodic minimal surfaces. We all know them, classic, our beloved gyroids. If you're trying to simulate one of these, your finite volume mesh is going to explode for the most part. And since we are not employing that mesh, geometric complexity is coming for free.
I see. I think I've seen some images about Hypergenic, like on Google, like when you type in Hypergenic and then you see all these complex shapes. What are you actually using them for? And the question that I'm aiming for is basically use cases. So can you name a couple of use cases in terms of structural mechanics or applications, as well as the CFD applications, where this is becoming rather useful?
Yes. Okay. So let me start by the complex shapes. We are known for these complex shapes, but complexity is only getting you so far. So some of these objects are, to be fair, showcases. So they're not necessarily, they weren't originally designed for full functionality, but now since we're employing our CFD kernel, our structural solver, in combination or in conjunction with our design kernel, we're able to go to devices or applications specifically in the field of advanced thermal management, lightweighting. So that is brackets typically. Brackets could be in super sports cars. They could be in, aerospace applications. And then the last thing that I want to point out is mainly actually only focused around the design portion of Hyperganic, which is a voxel engine that we also built from scratch over the past few years. That is consumer good applications or medical insoles, where we're actually starting to have a significant impact on the lives of people. One story that I really like to tell, and then I'll probably go back to the more engineering savvy applications, but it's still a nice one. One of our clients is a podiatrist in the APAC region, and by essentially employing our design tool, we were able to help him design much more advanced insoles, so inlays that you put in your shoes, so that one of his clients who lost all his toes in a serious hiking accident is now able to walk again properly, just because these insoles fit so nicely that he is not under pain anymore, and he's effortlessly walking again on these insoles. So it starts as small as just building a design tool that essentially allows people to, you know, design insoles, which is, it seems on the surface like not the most engineering type of application, but then there's actually quite a lot of thinking that goes into that. And then it leads all the way to, like I mentioned before, these bracket static, these static linear elastic stress strain optimized devices, where you say, I want to maximize my my strength to weight ratio. Essentially, I want to have a lightweight part, but I want to make it as strong as possible, while, for example, keeping the design intent. So that is, I could, for example, say, let me take a bracket, and I want to keep the surfaces of the bracket intact and infill the bracket with a latticing structure. But now, is this latticing structure going to hold? I don't know. What you can do is you can essentially then run optimization loops to selectively thicken or thin or slimmen these lattice beams so that they would support your load case optimally. And then lastly, to the, I would say, probably most exciting types of applications that we're seeing at the moment, at least for myself, since I have a background in the aerospace industry as well. These are these advanced thermal management devices, or in other words, heat exchangers, where we really start to see that highly complex, compact heat exchangers, where people want to employ structures like, for example, the TPMS structures that we've been discussing before, and additionally, actually, another point is they want to leverage also phase change fluids. This is really an area where we see increasing interest, and where we see increasing, where we can leverage our capabilities increasingly.
Yeah. Can you maybe quickly explain for the audience what do you mean by phase change in terms of heat exchanger?
A phase change is, think of your boiling water. If you're boiling water, by essentially introducing heat into your system, you're evaporating water. So the water changes its phase from liquid to gaseous, for example. And by doing so, you're essentially leveraging a concept that's called latent heat of your fluid, which allows you to store much more energy in your fluid than if you were to just stay within the same phase.
Yeah. I'm wondering, I haven't seen any structures of the heat exchanger designs yet, but I can imagine it's not the classical pin-fin heat sinks, or like the heat sinks that we usually like know from the old PCs, like that we've worked on as kids maybe, but it's like very, very complex structures. How do you make sure as an engineer, you know exactly which one to pick from a ton of different solutions that maybe your algorithm generates?
That's a very good question. Let me answer it in two steps. The first step is, why didn't we show them so far? Well, that has a simple reason. Since we are still developing our CFD, we haven't yet fully tackled the space of phase change liquids yet. We are able to simulate multi-phase flows, which means we can simulate the fluid dynamics of a mixture of essentially liquid and gaseous, but the phase changing process due to thermal boundary conditions is quite a complicated task, so we're still working on that, to be fair. But because of the methods that we employ, we have a predisposition to do these types of things, because the method that we employ is essentially very well suited to do these phase changing fluids. So that's the first part. The second part, obviously, is that some of these applications are in a very high value industry, and sometimes our customers also don't want us to show stuff. So for the most part, these types of things might actually be regulated so that we can't show them at all. Note to myself, we might actually just show some more of our work as a template or something like that on LinkedIn to show people what we're doing. And then to the second point, how do we select the right design? Also here, the answer would probably be twofold. One is sometimes people actually do have an idea of how they want the heat exchanger to look. So sometimes people just come to us, say, I have this heat exchanger. It is a gyroid infilled heat exchanger. Can you simulate it? It can be as simple as that. The second part could be, okay, now we have these options, and then we work with our customers and to find what is the optimization criteria, or what is the criteria to select the right application for their usage, essentially. So we know what they want, they know what they want, and we find the best solution together for the most part.
Yeah, well, it sounds so straightforward when you say it in the podcast, Moritz, but I can imagine as an engineer, you have like a multi-objective, like you want to optimize a multi-objective problem. You have a ton of parameters. How do you select ultimately the best design? Like, can you even, I don't know, type it in your software and saying like, I'm optimizing for a specific parameter or for a specific KPI, or how does that work in action? Because it sounds so easy. Like when you say it, it sounds easy, but actually it's a very complex engineering challenge.
It's true, yeah, it's a very complex engineering challenge. For the most part, we do restrict our solution space a little bit from the start. It's not like we're giving our optimizers the full range of all heat exchangers on this planet. That's what I kind of wanted to lead towards when I was saying, well, we work with the customer, right? So in the end of the day, we kind of, they know what they want and we get to know what they want. And so we're developing something that is very close to what they want, and then we're optimizing it for the sake of functionality. So in the example of a TPMS infilled heat exchanger, for example, if someone would say, hey, I want this heat exchanger and I want it to be infilled with a TPMS, well, then you're restricting your solution space or your parameter space effectively down to, let's say, 10 parameters, and then every multivariate optimization is much easier than if you were to employ, let's say, thousands and thousands of parameters.
Yeah, absolutely. I was interesting because you talked about in the beginning about design and basically the two solvers. Now I'm wondering from an efficiency point of view, how does your solution benefit, like in terms of time savings and resource savings, the engineering or end-to-end workflow? Like, do engineers even benefit from that, or like, what's the additional benefit of using something like your Hypergenic solution?
Again, very good question. I originally had planned to give a little bit of an introduction into how our technology works. I think now is a good time to do so. So essentially, one of the key benefits is that since we don't need meshes, and since we're employing a 3D discretization of discretization of 3D space in elements due to our immersed boundary method solvers, and we are also employing a discretization of 3D space due to our voxel engine. So our design kernel is based on voxels. We do not lose data between the two representations. So since we don't need to go through a intermediate step, we don't lose information from design intent to simulation and back. So that can be a significant advantage if you essentially do a multi-objective or multi-physics type of optimization, because you can pass your values in a different shape or form. You don't need to you don't need to modify your data, or you don't need to interpret data as much. You can essentially just move it between the two representations relatively easily. Then the second bit is, we all know CFD is expensive. It takes a lot of time, and due to our actually both the structural and the fluid solver can be optimized in terms of compute time. So that means you get to your results much faster. We haven't yet fully optimized them, but we are on a good track, I would say.
And then let's say an engineer would actually use your application. Like how would it actually work? So they have a geometry available. They would upload it, I guess, and then they could just pick from the solvers immediately, or what kind of or let's say preparation work they would need to do in order to get a first result.
So to answer that question, I would need to give maybe the audience and yourself a little bit of an update of how we are marketing our software. So generally, we do, like I mentioned in my initial introduction, we do have software that we're selling as a SaaS type of software. However, for the moment, we only offer design tools, so that is space filling algorithms in our product HyDesign, where people, for example, in the consumer goods space can select from various lattices and design objects in our cloud native tool, while the simulation solvers are not yet available as normal SaaS type of products like you would know from maybe some of our competing products. We are actually using them for our engineering services only so far, which has, I would say, two main reasons. One is we want to be sure that we tested and validated it as good as possible before putting it on the market. We want to make sure that the quality of our products is as high as possible, obviously.
Of course.
And the other side is that some of the things that we're just talking about are still under development, right? So it might not be fully ready yet.
I see. But I think you said you have some customers already using it. So I think from a marketing standpoint, it also has to be made clear that you have a functioning solution. Maybe correct me if I'm wrong. You have a functioning solution, but it's still in development, so to speak.
Well, specifically, for example, for lightweighting or structural optimizations, we are doing projects for our customers. So that's what I meant by solution. So they approach us with a problem, we solve the problem leveraging our technology, and then, for example, they would receive the end part, or they would receive a small app that automates a small part of their engineering workflow. On the CFD side, you can essentially translate it directly also there. It's someone approaching us, asking us for help, we help, and then we provide, for example, an end component.
I see. And the whole thing works how exactly? Like, is it a classical graphical user interface that we know of, like from other software vendors, for example, or is it like a low-code solution? Like, how does it actually work?
You mean how we are using our technology at the moment?
Exactly. Like, do you actually see something? Is it like just an API, or is it?
It's so far, for the most part, fully code-based. Also, one of the reasons why we haven't yet given it to our customers, because Hyperganic has tried in the past to give people access to a coding environment, and some people said they would like to use it, but it's just way too hard, and people hardly ever find time to learn a new coding language in their busy days. So that's one of the driving reasons why we're using it so far for ourselves. Apart from the reasons I mentioned before, obviously. On the other hand, HyDesign, for example, our design product is very easy to use, it's very accessible, it's a GUI-based tool, and we're really putting an emphasis on making it as easy and accessible as possible so that people that have never done something with lattices, for example, would be able to do, advanced latticing operations like merging multiple TPMS patterns into each other to create new patterns that have very interesting and exciting properties within, I would say, a few minutes only. So that's really where we want to go.
Yeah, that product that you just mentioned, like, where does it fit in the whole like area of products that you have at Hyperganic? Like, is that only for lattices? Like, you only have a graphical user interface for these lattice structures, and that's it? Is that correct?
Well, it's much more than that. We are embedding, for example, a lot of material data from our partners. We are in very good contacts with leading material manufacturers such as BASF. and we are implementing their materials as a starting point into our product. So that means effectively, if someone wants to, for example, leverage a certain powder-based material to, print a midsole, like the midsole I have here, that's actually made from that material. So if you wanted to get started with this type of midsole, for example, you wouldn't know how squishy, how hard is my material there. And so what we do here is we provide people with a library of validated materials so that they can easily infill their midsole and create something like this within a few minutes.
That's pretty cool. Yeah, I think one of the things we haven't talked about, Moritz, is maybe the thermal applications, so advanced thermal applications. Like maybe you could delve a little bit deeper into this thermal topic, especially for the nerds, the engineers listening to this podcast. Like what is actually possible with your tool stack?
Like I mentioned before, what we really focus on is the compact, high complexity heat exchanger, high performance heat exchangers that you would find, for example, in industries like hydrogen, sometimes in aerospace, sometimes in defense, generally high value industries where you want to save as much weight as possible because it translates directly into how much you're spending. For example, picture a heat exchanger is 1 kilo versus half a kilo. You launch it up into space. It saves you quite a lot of money doing so. So what we really aim for is, or what we're working also towards, since we don't yet have a full implementation of phase change fluids, I want to be honest here, is that we are aiming for these types of applications, and we're working so far in the space of applications where we have compact, complex heat exchangers that leverage so far incompressible low Reynolds number fluids. So these are, like I said, these types of heat exchangers, or another group of applications would be control manifolds, where you have highly pressurized fluids, where you really directly benefit from the fact that our fluid simulation, is a coupled simulation between fluid dynamics and thermal analysis. So that means we are doing both at the same time, really.
I see. Okay, yeah, that makes sense. I also appreciate that you are like super honest in the podcast, because I know, especially in the startup space, like other companies, they always say like, we can solve everything, like we have solved it, but in fact, like when you use their products, it's not the case. So yeah, props to you, Moritz, for actually being honest here. Not sure if we have missed anything. Maybe you can talk a little bit about the area of consumer goods, like what you do in that area, in that space.
For consumer goods, we have essentially 2 or 3 main industry verticals that we're satisfying or that we're working in. One is the orthopedic, for example, orthopedic devices such as insoles. We have strong partnerships in that area. I explained this very nice story of one of our customers that was able to help one of his customers to improve his life. So what we do there is we provide apps. Think of these as something similar to HiDesign, our web native design tool, but we provide these apps as a standalone solution for this specific client. This, by the way, holds true for pretty much all the areas that we touch. We are always open to provide apps to some of our customers. So that could be in the space of thermal management, that could be in the space of lightweighting. That is true for the space of consumer goods. Another area is that we partly automate workflows. So, for example, with one of our customers, we had developed an app where you can picture it as a daemon application. So you don't have a a user interface per se. You actually just feed it input data and it outputs you a final design. So that is, you say, hey, I have a scan of my feet, for example, and out comes a insole that would be printed and shipped to your house direct to consumer. And then the last space is generally advanced cushioning, these types of solutions like saddles, midsoles, you name it. I think some of these applications are quite a hype, I would say, in the 3D printing industry. And some of these applications actually really do make a lot of sense and have an impact on the lives of the end consumers.
Yeah, super cool. What's coming next for Hyperganic? Any sneak peeks for the audience?
Yeah, thanks for asking that. I mean, in the end of the day, I already kind of illustrated what we're working towards. What we really see as our core strength is this multi-physics optimization. We see some early, some later indications, some validations, and some first success cases out there now. We're working very hard on our both structural and fluid solver. And in the end of the day, we're really hoping to we're really aiming to make a difference in the engineering industry in making the hard stuff a little easier.
Definitely. Like people should actually check out, like if they Google your name, like Hyperganic, what kind of structures you actually create is pretty awesome, pretty amazing. Can academics also try it out? Like, do you kind of have an academic program? Because I know the question will come, and maybe you get a private message on LinkedIn. So can academics like use it to some extent?
Well, we get a lot of requests. I think it depends on a case by case decision. In the end of the day, we have, for example, like I illustrated before, a good partnership with TU Munich. We are quite a small team, I would say, so we always need to focus on the things that really matter. But if it so turns out that people who want to use our tools are very self-sustaining, then I guess there's probably not much we can say about it. But always feel free to reach out to me. I'm quite a responsive person in general.
No, that sounds good. So I'm going to put your LinkedIn link down in the description so people can reach out to you.
Yeah, definitely.
Anything we might have missed, Moritz? Anything important? Maybe some closing remarks from your side before I wrap it up?
Yeah, first of all, I wanted to say thanks for having me on this podcast. I think it was a very interesting discussion and very good questions. You really go to the essence of what people say, so I like that. But apart from that, I think we covered everything that is important about our work at the moment. But I would really emphasize, keep pumped on what's coming. I'm personally extremely excited. I'm sitting in the office even on a holiday today. So that's what it is, I would say.
Definitely. And I think the next step for me would then be to interview Lynn, so the actual founder of Hypergenic, if I'm not mistaken. Lynn Kaiser, right? Yeah. I have to interview him as well. Maybe he can talk about a little bit of the background, like how he came up with the idea of Hypergenic. And I'm going to be your personal accountability buddy to make sure that you post more amazing stuff on LinkedIn, Moritz. So I'm going to hold you accountable.
Yeah. So, I mean, Lynn is working on his new venture now. He's not part of Hypergenic anymore, but I would be curious to see what he says about Hypergenic and how his new venture is different and what he sees for his future. Obviously, I wish them all the best. And it's exciting. More people in the space means more attention to the things that matter.
Absolutely. Okay, with that, we wrap it up, Moritz. It was an interesting discussion. Thank you so much. Maybe there will be a second part. Like once you have solved some other cool, amazing problems, maybe there's going to be a new solver, who knows? Then you can always hop back on the podcast.
For sure. We'll post more interesting things, so we'll have more concrete stuff to discuss next time.
Awesome. Appreciate it. Cheers.
Cheers.